Hello, welcome to this presentation as part of the IGS Hydraulics Technical Committee session on canal lining. The title of my presentation today is The Use of Geosynthetic Cementitious Composite Mats, or GCCMs, for lining irrigation canals as an alternative to conventional concrete. My name is Will Crawford. I'm a director and co-founder of Concrete Canvas Limited. And I'd also like to introduce and thank my colleague Lee Church, Technical Manager at Concrete Canvas, for his contribution to this paper and this presentation. And I'd like to start by reiterating the importance of solving the very real and pressing issue around water scarcity and seepage losses in canals. As Bob Kerner said in his lecture on geosynthetics and hydraulic applications, the scarcity of fresh water will soon become very contentious amongst all natural resources. At the same time, we know that about a third of water is lost during transportation in canals. This is based on data from a 2006 census by ICID. So this presentation will look at potential solutions to these problems. I'm going to start by summarising briefly what the current challenges are. I'll then look at how GCCMs can help solve these challenges. And finally, I'm going to show you an example of where GCCMs have been used in a real-world application of canal lining. So Hervé has already covered some of the issues with conventional concrete lining in his presentation, and they're also detailed in his 2017 paper with Giroux. In summary, whilst concrete as a material can have very real benefits, it is extremely hard-wearing and durable, for example, it is also prone to failure on channels that are incorrectly designed or installed. The images shown here are good examples where freeze-thaw and ground heave have led to concrete cracking. This cracking leads to water seepage, and this in turn can lead to a multitude of problems. For example, salination of soils, waterlogging of the surrounding area, and ultimately undermining of the concrete structure itself, which can lead to complete collapse, as shown in the images here. In addition, conventional concrete can be challenging from an installation point of view. Firstly, it can be time-consuming, especially when compared to geosynthetic solutions. And when maintenance shutdown times are short, as often is the case in critical canal infrastructure, this can severely limit the scope of work. Secondly, on-site quality control can be an issue, especially in some less developed parts of the world, and poor quality concrete mixes can exacerbate the issues highlighted above. And finally, the nature of pouring concrete means that side slope angles are limited. Typically, slopes above 1 to 1.5 gradient require formwork, and this leads to additional installation time and cost. So why is concrete still used for this application? As Hervé and Giroux point out, concrete linings remain the preferred method of lining canals because engineers and agencies are familiar with concrete linings. And for all its drawbacks, concrete does have its benefit. It's hard, it's durable, it's UV resistant, it can be easily maintained, it can be trafficked by cattle, and it's less prone to local theft or vandalism. So how do we combine the benefits of concrete with the speed and ease of installation of a geosynthetic product? And that is the aim of this new class of geosynthetics. Defined within ASTM D4439, the GCCM is a factory-assembled geosynthetic composite consisting of a cementitious layer contained within a layer or layers of geosynthetic materials that becomes hardened when hydrated. The most common GCCM is called concrete canvas, and it consists of a fibrous polyester top surface overlaying a reinforced fibre matrix embedded within a high early strength dry concrete mix with a water impermeable PVC coating on the rear surface. GCCMs are supplied in roll format and they're laid over the soil structure that they're designed to protect. Once in place, fixed and jointed, they can then be hydrated, typically by spraying with water. The concrete then sets hard and typically is ready to use within 24 hours, providing a water-impermeable membrane overlain with a protective fibre-reinforced concrete covering. Roll formats vary from bulk rolls, which are typically 1 metre wide and up to 200 metres long, to man-portable rolls, to wide rolls, which come in a multiple of the standard roll width. Typical applications include lining water channels, protecting slopes from erosion, lining culverts, and resurfacing old concrete structures such as channels or lining reservoirs. One of the key properties of GCCMs is their ability to accommodate high levels of ground deformation while continuing to provide impermeability and effective erosion control. This is due to the composite nature of the product, where the fibre reinforcement initiates microcracking within the concrete. This allows relatively high strains to be achieved with minimal cracking within the concrete itself. This behaviour is demonstrated by the stress displacement graph on the screen now, where, after the initial break, an incremental sawtooth-shaped rupture is seen as the concrete and fibres are subsequently loaded, prior to the final rupture itself. Effectively, this means GCCMs can deform by up to 5% without compromising the impermeability of the membrane or the protection provided by the concrete. While this may not seem like much in the world of geosynthetics, this is in the world of concrete. And this has obvious benefits when you look at the issues faced by conventional concrete lining, such as ground heave and freeze thaw. I'd now like to move on and look at a real-world application of canal lining using GCCMs in the La Serena region of Chile. This is a project over 2 phases, with the first phase starting in 2016, which, based on its success, led to a second phase which was completed at the start of 2018. So what was the problem? Well, the existing Bella Vista Canal was cut into soil and rock, as you can see on the right-hand photo, and, unsurprisingly, was suffering from high levels of water loss, and this was reducing the amount of water supply available to the local community. There were 5 sections of canal identified for improvement, which were all in difficult to access locations. Another key challenge on this project was that they could only cut off the water supply for a period of 8 days at a time. And this was only possible over a short period during the winter months. Otherwise, there was a risk of damaging the water supply and crop failure to the local community. The solution selected was a 5mm GCCM manufactured by Concrete Canvas called CC5. The selection was based on the speed of installation compared to conventional concrete linings and the ability for it to be transported to the sites where access was limited. It was also felt that it was more durable and there was lower risk of theft and vandalism compared to geomembrane solutions. You can see from the photo here that it was applied in man-portable rolls cut down in lengths to suit the dimensions of the profile. And this first phase of the project was completed in only 5 days by a team of 6 people covering 600 square meters. This included the ground preparation, which involved substantial reprofiling of the canal, as well as the laying of material. Based on the success of this first phase, it was then decided to go ahead with a much more substantial second phase, covering a further 2.4 kilometers. And you can see just before I move on the images before and after installation. For this second phase, a more uniformly graded profile was required, and so a new method of ground preparation was used. This involved using a trapezoidal former to create a precise channel profile, and by compacting stabilized material behind the former, this allowed the canal fall and the profile to be precisely controlled. This profile was then overlain with the CC5 GCCM material, laid transversely across the channel, and on this second phase of the project, access was better, and so the material was delivered to site in bulk rolls. These were loaded onto spreader beams and deployed by hanging the spreader beam from the available excavators on site. Once laid, the edges of the GCCM were fixed into anchor trenches using ground pegs, and subsequent layers of GCCM were overlapped by 100 millimeters, shingled in the direction of water flow, and the joints were then secured using screws with a polyurethane sealant. Where the GCCM interfaced with existing infrastructure, such as head walls, the material was secured using concrete screws and anchor bolts, and where necessary, this was sealed with the use of an adhesive sealant to reduce ingress. I'd now like to show you a short video which I think demonstrates the application process much more effectively than just the images. You can see here the trapezoidal formwork being moved along and the GCCM material being unrolled transversely into the channels. Due to the logistical challenges of only being able to work for 8 days at a time on this project, a team of anywhere up to 70 installers worked on the project at any one time, working along the 2.4 kilometre channel in sections. So in total, they had 3 of those trapezoidal formworks, they had 11 backhoes and 3 20-ton excavators, as well as spreader beams on site. So while one team worked on regrading and preparing the substrate, another team was laying material further down a section of the canal that the preparation team had just completed, and so forth. And this allowed the installation to progress at a much quicker rate than it would otherwise. Using this method, a total of 18,000 square meters of CC5 GCCM was installed over 40 days, with the team working around 9 hours each day. And as a result of the project's success, the client subsequently specified concrete canvas GCCM for another similar project. So just before I conclude my presentation, I'd like to look to the future. One of the limitations with GCCMs is that although they have a fully impermeable backing film, they still rely on mechanical methods of jointing, such as sealants and screws. There is now a new variant that aims to address this issue, called a GCCB, a geosynthetic cementitious composite barrier. And this consists of a GCCM with an additional 1 mm geomembrane laminated onto the rear surface. This now allows for a fully testable, thermally weldable joint, providing a solution with the same impermeability as a welded geomembrane solution, but incorporating a protective concrete top surface. That concludes my presentation. I'd like to thank our partners in Chile, Pacifictech, who provided the images and the video for the Bella Vista case study, and they were also responsible for the installation of that project. And I'd also like to thank the session chair, Eric Blond, for the opportunity of presenting today. Thank you very much.